What is going on, guys? Welcome back to the Python data structures tutorial series. In this video today, we're going to learn how to implement the hash map data structure in Python from scratch. So let us get right into it. Alright, so we're going to implement the hash map data structure from scratch in Python today, and as always I want to start by giving you a theoretical explanation of what a hash map is and how it basically works before we jump right into the coding, and as always we're going to do that here in MyPaint. Now, the basic idea of a hash map, or also oftentimes called hash table or dictionary, is that we have so-called key value pairs. So we always have some key, like key 1 for example, pointing to some value 1. And every key can only have a single value. Now values can occur multiple times, but keys are unique. So key 2 can point also to a value 1, but we cannot have key 2 then pointing to something else. So I could have key 3 pointing to value 2 or whatever. That's the basic idea. We have a key and this key leads us to the value. This is the principle. This is how it works in general. The interesting thing about a data structure is, of course, how does this work? And this works with a hash function. This is why it's called a hash map. And it works by passing a key into a hash map, into a hash function, and as a result getting an index where to find something. So we're going to implement our own hash function in this video today, but let's for now just consider the hash function to be a magic black box. All we do with this hash function is we feed in a key, some key 1 for example, and as a result we get a position in a list, in an array. So we get some index. And this is deterministic. For the same key, I'm always going to get the same index. And the idea now is that the key is basically what I input into the hash function to get a calculated result, so I don't have to iterate, I don't have to search, I don't have to go through all the possible branches of a tree or something. I just calculate an index based on the key with a hash function. And this index then leads me to a position where I can find a value. So if we consider that we have some basic list here with elements 5 and 10 and 30, and maybe we'll also have some strings here like Mike, and maybe we have, I don't know, some booleans here like true or whatever. Doesn't really matter. We have some elements in the list here, and instead of providing now the index, what I can do, of course, is I can say I have index 0, 1, 2, 3, 4. Instead of saying I want to find the value Mike, or I want to find the value at index 3, which is of course also simple. If you know the index, you can just jump to the index, but if you don't know the index, you have to search. And what we do now with a hash map or with a key value pair is I have this hash function. When I input the key name, for example, into this hash function, as a result, I get 3. That's the basic idea. Now, why do I get exactly 3? It doesn't really matter. Let's say I don't have Mike in the list yet, and I want to store the name. So I want to store the value Mike with the key name. So what I do is I feed the name into the hash function. As a result, I get 3. And what I do then is I place Mike at this position. That's the basic idea. Why do I do that? Because the next time I want to find Mike, I want to find a value for the key name, I just have to do the same thing. Hash the name, get 3 as a result, and instead of looking through all the positions here to find Mike, I just know, okay, position 3. Jump there immediately. So in the best case, or in a good case, in a convenient case, this can be done in constant time. Constant time. Why? Because that's just a calculation here. We're going to talk about this here, but this is just a calculation. I get the key and jump to the corresponding index. I don't have to iterate over the elements. It doesn't matter how many elements I have here. If I have a unique position for every input here, I can just jump there. Practically speaking, there are some difficulties, and these difficulties are that hash functions produce different values, produce the same values for different inputs. So maybe I have the key, I don't know, job or something, and for some reason, again, let's consider this a magic black box. For some reason, when I feed job into the hash, I also get 3. So this is called a collision. This means that, for example, if I want to store the job programmer, what's going to happen now is that it's going to recognize, okay, index 3, but it's going to see, oh, I already have a value here. And the question is now, how do I resolve a collision? This is called collision handling. So collision handling, and it can be approached in different ways. One way, for example, is if I have a fixed size, let's say I have, for example, here some empty space, and then again some value, would be to just jump to the next free position. So it would be something like, okay, I already have Mike in here. I want to store programmer for job. So what I do is I jump to 3. Okay, 3 is already taken. Let's go to the next one. Oh, 4 is also taken. Let's go to the next one. Oh, this is free. So let me store programmer here. That's the basic idea. I jump until I find a free spot. And of course, what happens now is that if I want to find programmer, if I want to find job, what I do is I say hash, I see 3. I see this is not what I'm looking for. This is also not what I'm looking for. This is what I'm looking for. So I'm jumping again. So practically speaking, if I have a good hash function that gives me good indices for the different inputs, I can expect to have constant runtime on average. However, in the very worst case, what's going to happen is that I have a list with a couple of free slots. And let's say my hash function is very stupid. Every time I put something into it, every single time it produces 1 for some reason. For job, for name, for age, for anything that I put in here, I get 1 as a result. What's going to happen then is everything is going to be placed at 1. So I'm going to have stuff like Mike, I'm going to have stuff like programmer, I'm going to have stuff like 30 and true and all this stuff. And every single time I want to look up something, I'm going to land here and have to jump through all these elements to find my element. So in the worst case, I'm going to end up with linear runtime complexity. In the very worst case, I have to go through all the elements until I find my element. That's the worst case. But with a good hash function, we can get an average case of constant time. Average case complexity, which is constant. Now, we here are not going to use this collision handling. In our implementation, we're going to use buckets, which means we're going to have lists of, or we're going to have a list of lists. So instead of having slots, I'm going to have lists. And this means that if I now try to input for name, Mike, for name, I try to hash and I get 3. What's going to happen is I'm going to add Mike in here. So I'm going to say that my list here now is going to be Mike. And when I get the new value job, or the new key value pair job programmer, and for some reason my hash function gives me a 3 again, I'm just going to append it to the list. So I'm going to say programmer. And that is going to be how I handle collision. So I'm not going to just shift it. So to keep the size dynamic, we're going to have these buckets. But that's the basic collision handling that we're going to do. We're going to have multiple values. And then, of course, if I land here, I have to iterate over them until I find the element that I'm looking for. That's what we're going to do here. This can still, of course, lead to the problem of worst case linear runtime complexity, because all of the elements can end up in the same bucket, and then you just have a list. Then you just have to treat it like a linked list and look at all the different elements in there. This was a little bit longer of a theoretical explanation now, but I think it's important to understand how this works and why this works. And now we're going to implement this. Now we're going to write the corresponding Python code for this. So I'm going to say here hash underscore map py, and we're going to create a class hash map. So this time we don't have a note. Finally, we have just a single class hash map. And what we're going to define here in the constructor is we're going to say a hash map starts with a capacity. Now, for Python purposes, this is not really that much of a difference, especially with our buckets implementation, because if you use something like C, you would have to, or any language that has fixed sized lists, you have to keep track of the size, and you need to make sure that you don't exceed the capacity. In Python, it's not really an issue. So in our case, this is just going to be how many buckets we have, but the buckets have limitless capacity. I mean, of course, you have a RAM limitation, but programmatically speaking, I can have buckets that are very long. So the capacity is just going to be the number of buckets in our case. But if you're implementing this in C, you want to take care of the capacity of the size, and you want to resize maybe if you want to keep this dynamic. But here now we're going to use the convenience of Python and just say the capacity is the number of buckets. And besides that, I can store an infinite amount of elements in my hash map. So self capacity, and then we're going to say self capacity equals capacity self dot size is going to be equal to 0. The difference here between size and capacity being capacity is the number of buckets, size is the number of elements in the hash map, and then we're going to say self.buckets is going to be empty lists for placeholder in range capacity. There you go. Okay. So that's just the initialization. Let's start with the basic stuff again. We're going to define the methods that we're going to use. So we're going to have obviously a length method or a dunder length. I'm going to pass for now again. I'm going to have a representation dunder. Or actually we don't need, do we need a representation dunder? I don't think that I implemented one in my prepared code. So let's actually just print the buckets if we're interested in that. Let's not use the representation, but we're going to use the contains dunder. So to see if something is part of the hash map, for this we're going to do it in the same way that Python dictionaries do that. We're going to see if we have a key present. So actually we need to also say key here. Then we're going to have put. The operation put means we're putting in a new key value pair. So key and value are going to be part of that. Then we want to have get. Get means we provide the key and want to get the corresponding value. And then we want to say remove, which is going to remove the value or the key value pair for a certain key. And then we want to have these typical dictionary methods. We have keys. We have values, and we have items. This is the same that we have in a dictionary in Python. So keys will give us the list of all the keys, values of all the values, and items will give us the key value pairs. And then we have one important function, the most important function, the black box here, which is our hash function. I'm going to make this private with an underscore here. That's just going to be a helper function that's in the class. And this is going to take in a key and return the index, the position. Now for this here, you can use whatever you want. It just has to fit certain properties. You need to produce, as a result of this function, you need to get an index that's part of the, that's within the capacity. So if you have a hash function that produces values like 5,000 or maybe even with characters in them, that's not what you want to have. You want to have a hash function that gives you an index that's smaller than the capacity. But besides that, it doesn't really matter what you do here. Of course, it matters in terms of performance and runtime complexity, but it doesn't really matter in terms of it works. But of course, an intelligent hash function will lead you closer to the ideal of having constant runtime complexity. And if you use a very bad hash function like always returning 0 or always returning 1, you're going to have the problem that you're ending up with worse average runtime complexity. So our hash function is going to be a simple polynomial rolling hash. We don't need to really get into this too much, but the basic idea is we're going to create a string version of our key. So I'm going to say key string is going to be equal to str key. And we're then going to iterate over the individual characters, get their ASCII codes because we need to work with numbers. So we are going to allow strings as keys as well, but we're going to have to use the ASCII codes to do calculations because we need to work with numbers here. So key string is going to be string of key, and then we're going to say the hash result is going to be 0 in the beginning, and we're going to say for every character in our key string, we're going to say that the hash result should be equal to taking the current hash result, so in the beginning 0, times 31 plus, and then the ASCII code of the character, and the most important thing, modulo self.capacity. Why is that so important? Because by saying modulo self-capacity, we will never get the capacity or larger, we will always have a number that is between 0 and capacity minus 1. So that is exactly what we need. So anything modulo self-capacity will be good or will be functional. It won't be necessarily good, but that is what you need as a hash function. So something that gives you a value between 0 and capacity minus 1 as a result of a key. And of course, deterministically. So generating a random int between 0 and this capacity minus 1 boundary doesn't do it. You need to always get the same result. Yeah. So that's our hash function here. And now we can get into the implementation. For the length dunder, it's quite simple. Just return self.size, which again means we need to keep track of that. For contains, it's also quite simple because since we're going to have, we're not going to use the keys function here. We're going to say for each bucket, we're going to see if the key is there, if we find the key. So we're going to say here, index is equal to self.hash function key. And we're going to basically go to the bucket. So bucket is equal to self buckets index. And then if we have multiple elements in there, we're going to just say for key value pair in this bucket, if key is equal to key, what I want to do is just return true. Otherwise, return false. Basic idea is I use the hash function to calculate the correct bucket. If there's just a single element, then I'm going to see if that's the correct one. Otherwise, I'm going to try to find it. The important thing is when we add something to the bucket, it's always the key value pair. It's not just the value, because then we cannot know what the correct key is. We need to have both the key value pair in there so that we can actually compare the keys. And in this case, I'm just looking for the correct key. If I find it, the element is part of the hash map, otherwise not. So return false. A similar thing can be done for the get function. So the get function is actually exactly the same structure. Only difference here being that we don't return true or false, but we return actually the value. And otherwise, we raise a key error. So key not found. So again, same idea. I get a key. I try to find, or I get the index, which is determined by the hash function. I go into that correct bucket. And if I find the corresponding key there, I return the value that belongs to the key value pair. That's it. And otherwise, I see key error because the key that you're looking for is not found. The put also works not too different, but here now, of course, we don't return, we create. So again, we can say, we can start in the same way. We need to calculate the correct index and we need to find the correct bucket, but this time we're not looking for something, we're appending something, or we are creating something. So we need to say here for I key value and enumerate this bucket. So we enumerate all the elements in the bucket, and the idea is if I already have the element in the bucket, I want to update it. If I don't have the element in the bucket, I need to create it, so I need to append it. How do we do that? We can use a fancy thing in Python called for else. I have a video on it. If you don't know the feature, this is quite interesting. If you break out of a loop, if you break out of a full loop in Python, you just break out of it. But if you don't break out of it, if you leave it without breaking out of it, you can go into an else branch. This is a feature of the language. So I'm going to show this here in a second. If the key is equal to the key, we can update the value of this key value pair. So we can say bucket I, so bucket at the position that we're at, is going to be equal to key value. So to the new key value pair. The key is going to be the same, obviously, since we have this if statement, but the value is going to be whatever we pass here. So if it already exists, go there, change it. Otherwise, or maybe, not maybe, what we're going to do here now is we're going to break out of the loop, and we're going to append here an else branch. And in this else branch, we're going to say bucket append key value. So for those of you who don't know this feature of the Python language, this means that we're only going to get into this else branch if we leave the for loop without breaking. So if I go through all the elements here and I don't get to a break statement, then I'm going to go into an else branch, or into the else branch. If I break out of the loop, I'm not going to go into the else branch, which means basically if there is no key, or if this key doesn't already exist in in the hash map, then I'm going to just append it. Otherwise, I'm going to update it and break out of the loop. That's the idea. And of course, don't forget, if you add a new element, self.size has to increase to guarantee that we can do this here in constant time, because otherwise I have to iterate and count. And if I always just update this, I just have to look it up. All right. For removing it's now basically the same as getting, but we need to delete the element if we find it. So I'm gonna just copy the code of the get method here, and we're gonna say index bucket again. If you find the key, what we're going to do is we're going to delete, or actually before I do that, I need to be able to say which bucket element I want to delete. So again, I, and then this in enumerate bucket. And this allows me to say, okay, I'm in this position or at this position where I find the key, and I'm going to say delete bucket this position. Self size is obviously going to decrease by 1. And the important thing again, I want to break out of the loop. If I don't break out of the loop for some reason, it means that I don't find the key. So I raise a key error. So I remove the key from the bucket, and if I don't find it, if I don't ever get to this section here, it means the key doesn't exist, so I raise a key error. All right, so that's remove, that's the get, that's the put, and these are now not too difficult. All we have to do here is a simple list comprehension, because I just have to say k, so the key, for bucket in self buckets for, and then key, and you can say value or just placeholder in bucket. So this says go through all the buckets, get all the key value pairs, and give me all the keys. I can copy that, I can paste it down here, replace this by v, make this a placeholder, make this a v, and I can also then copy paste this. And here I want to return both key and value for bucket, key value in bucket. And that's basically it. Now let us talk again about the runtime complexities. So for this one, obviously I don't think we need to talk too much about this constant. I just have to look up the value. Regardless of the size, this is going to take the same amount of time, constant, always. Contains now, and actually this belongs now, or this is now true for contains, for put, for get, and for remove. They all have, they all have linear runtime complexity in the worst case, because of the thing that I explained here with the, all of them could end up in the same bucket if you have a bad hash function or just very bad luck. But otherwise, you're going to have a good distribution. And because of that good distribution, on average, you're going to get constant runtime complexity. So for all of these, we have an average of O of 1 constant time, but a worst case of O of n linear time. And this depends on the quality of the hash function. We can copy this and we can paste this above all these functions. Every time we have to go to a bucket and find the correct slot, that is worst case linear and average case constant. What we should say here, and by the way, this also, or actually for this, let me just think about this. We go through all the buckets. No, this actually has linear runtime complexity because we have to go through all the buckets, all the elements. So these three are linear every single time. This is not about worst case. This is also about best case and average case. We have to go through all the elements, all the key value pairs. Otherwise, we can't do that. So this is linear. And the interesting thing now is I always say here constant. And it's true, it's like constant in terms of n. So it doesn't matter how many elements, how many key value pairs I have. On average, it should be constant. But it's not entirely true because what you see here is we iterate over the characters of the string. So technically speaking, this function here is O of k, you could say, So linear in key length, which means that the longer your key is, the larger the effort, or the more effort this function will have. But usually you don't use like extremely long keys, so you can ignore this. We could say, practically speaking, we have O of 1 if we don't consider the key length. But if you want to be precise about this, the key length, the amount of characters in the key, influence the runtime complexity of the hash function. And since we use the hash function in every single function here, we should say it's average O of k if you want to be precise, but O of 1 is fine. So constant time. All right, so let's play around with this. Let's say if name is equal to main, what I'm going to do here is I'm going to say hash map is equal to hash map. And now I can put some stuff into there. So I can say hash map append, or not append, sorry, put. And I can do stuff like name Mike. And I can say age 30. And I can say job programmer, and so on. And what I can do then is I can say print hash map dot items. And I have a problem here. Capacity, of course, yes. Sorry, let's go with 32. Orc, where did I use orc? Oh, sorry, ort, ordinal. So ASCII code, ORD. What else? List indices must be integers or slices. Yeah, sorry. We need to also, of course, return the hash result. If we don't do that, we know what the index is, but we don't actually return it. There you go. Now it works. So we have name, Mike, job programmer, age 30, and we can also see what the internal structure looks like. So I can say hash map and then buckets. And you can see in this case, I am quite lucky, or actually not lucky, this is to be expected, but I have a separate bucket for each of them. Now, the more values I add here, the more overlap I will have. So the more I will get into buckets that have multiple elements, especially because I only have 32 buckets. So at the latest point when I have like 33 elements, I'm going to have buckets that have more than just one item, but probably before that. So to show you how this works, or to see how good my hash function is, what I'm going to do now is the following. I'm going to say import UUID, which is a Python package or Python module that allows me to create these unique identifiers, which are just strings. And I'm going to say import matplotlib.pyplot SPLT. This is now no longer a tutorial about the data structure, just showing you how well it works. What I'm going to do here now is I'm going to say I want to have a hash map. This hash map should have a capacity of 100, so 100 buckets. And I'm going to say now for placeholder in range, and I'm going to use 1,000,000 elements here. So I'm going to add 1,000,000 different keys to this hash map. And I'm going to say hash map put UUID 4. So this is just a long string, and probably unique, most likely. And the value doesn't really matter. I'm just always going to add the same value. But I'm going to place these different identifiers into the hash map as keys, and we're going to see how well they are distributed. If I have a bad hash function, this is not going to be evenly distributed. If I have a good hash function, it should be like pretty similar. So I'm going to say here x is equal to an empty list, y is equal to an empty list, and then I'm going to say for I bucket in enumerate hash map dot buckets. And here now I'm going to say x append I, just so I have the bucket number, and y append the length of the bucket. So how long is the bucket I? So that I have the lengths of the buckets, I want to plot them as bar plots. So I'm going to say plt bar xy plt show. And when I run this is going to probably take some time here. Maybe I should do it with less so that we don't have to wait too long. Let me just cut this off. Let's go with 5 here and 1 0 less. Actually, it's still running, right? Can I not? Oh, there you go. So this shouldn't take forever. But basically what I'm doing is I'm going through all the buckets, through all the 100 buckets, and plotting how long they are. So how many elements of the ones of the 500,000 in this case that I added end up in this bucket, and how many of them end up in the next bucket. And if I have like roughly the same height for each bar, this signals that I have an even distribution with my hash function. So I don't know what's happening here. Let me just run this maybe with even less, just to see if it works. Okay, so this was not representative because I didn't use a large amount of values, large number of values. But there is something in statistics called the law of large numbers, which means that the more elements you have, like the larger the numbers, the more you're going to approach, the more you're going to converge to the expected thing. So I think that with this hash function here, the more values I have, the more they're going to be evenly distributed. So actually this is not what I wanted to do. Let me add a 0 here and see if it gets better over time. But you see that the distribution of the bucket lengths, or the different bucket lengths, are not too different, which means that the hash function is decent. Because there's no bucket that's like super small or super large. It looks like they have a somewhat even distribution. So the runtime complexity here, yeah, I mean, it depends, because of course when we have the size limited, we probably have linear runtime complexity divided by something, which is still linear. But if you have enough capacity, you should have constant runtime complexity. So if I make this 1,000, it should get better. It should also be faster because I have more buckets and I have to do less of the searching, of the linear search. But yeah, this is fundamentally how you build a hash map in Python from scratch. We talked about the runtime complexity. I think this is a very important data structure, a very useful data structure. Also, if you do lead code challenges, oftentimes a useful data structure. Of course, in Python, you're going to use the dictionary usually. So just dict to create an empty dictionary, or if you want to initialize it right away here, key value. This is what we usually are going to do, but that's basically behind the scenes, just a hash map. So yeah. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.